All right. Well, I'd like to welcome everybody again to the June Indicator Behavior Working Group session. Again, I'm Charlie Frick, your chair, and thankful again to Dee Scher from Oasis and the Open Cybersecurity Alliance for creating this working group and giving us the opportunity to meet. Today's agenda, I have a couple high-level overview things to address for the overall working group management. And then we have an interesting technical talk today from Mr. Michael McPhail of MITRE on applying detection engineering methods for industrial control systems. And then I wanted to save us a little bit of time at the end for some general discussion, just capturing some feedback, as I know a lot of folks just got back from RSA and wanted to kind of collect some insights. For just the top level logistics notes. So right now, Ladrina isn't here today. She might be away from the working group for a while. So in the meantime, I'll be handling chair duties solo. If we do want to look at electing an additional co-chair or selecting, very open to that. And if anybody's got a deep interest, let me know and we can coordinate that. Just feel free to reach out afterwards. You can hit me on the Slack channel. And additionally, for today in the Zoom chat, I'll share this, but on the IoB working group GitHub site, where we place a lot of our, our reference implementations and other discussion and our charter, I also have put together a set of slides. It's as a PDF. If you ever want to share stuff about the IoB working group with other folks, this link in the chat will essentially get you the link to access the Slack, outlines the email address for joining the IoB working group, gives some high level data on how often we meet, and provides some of the general rules of the road, standards of conduct that I leveraged from the main OCA site. And feel free to share that and use that if you have anybody that that's interested in the working group. Now, with that aside, I would like to kind of dive right into Michael's talk so that we can, have plenty of time for him and also for any Q&A. Michael, if you're good, I'd let you give you a moment to introduce and have right at it, sir.
All right, thank you. I had to find the mute button. Can y'all see my screen?
Yes, we can. And also, everyone, if you have questions in the chat, I'll be sure to forward them to Michael, as I can attest, it's always hard to brief and read at the same time.
Yeah, thank you. I appreciate that. So my talk today is on applying detection engineering methods to industrial control systems. So a little bit about me. My background was originally in enterprise or IT security. I'm doing a lot of detection engineering work. I was at MITRE for a long time, working for a number of government sponsors. A few years ago, I went and did a stint at a startup doing ICS security and did a lot of detection engineering work, as well as a bunch of other things. Then I returned to MITRE a couple of years ago, where I've been doing, again, industrial control systems, detection engineering, and threat hunting related work. So please feel free to jump in and ask questions throughout this. We can take this whatever direction is most valuable for y'all. So industrial control system security covers a lot of critical infrastructure, everything from electric generation and transmission to wastewater processing, advanced manufacturing, building automation. So there's a lot of different verticals or kinds of industries that we're interested in within this umbrella of ICS. So today I'm going to talk about detection engineering and the challenges we face in the ICS space. And some of those problems are the same as what we're dealing with in IT or in enterprise security, and some of them are specific to our ICS problem space. So when I say detection engineering, I mean the process by which we decide what kinds of activity we want to alert on in an environment to detect some adversary behavior. We need to figure out, what kinds of questions we want to ask of the environment, what kinds of data we need to collect. And then additionally, after we have some alert, we need to figure out what context the analyst is going to need to be able to actually deal with that alert and process it appropriately, right? Determine if it's malicious or benign. So I'll talk about some of the challenges we're facing and then get into some of the ways I think we can solve those challenges. Oftentimes I see detection engineering or detection in general reduced to a set of functional requirements for a product, right? We need to detect firmware changes, or we need to detect adversary discovery activities in the environment, those kinds of things. So that's useful from one perspective, and it's valuable, but I think we need to get beyond that community and be able to talk with rigor about what we're detecting, what our coverage looks like, where we have gaps in our detection, and where we have detection in depth, which is something we should be shooting for. So often we're using threat intelligence as a starting point, but then we're taking a collaborative red team plus blue team approach and using purple teaming to really rapidly iterate on detection and analytic development. And some of these models, in some organizations, you have maybe a threat hunting team that comes in for a short period of time and characterize the environment. They look for some malicious activity and then they leave. And in other cases, you've got a dedicated SOC that's doing persistent monitoring and continually updating their information about what's going on and looking at new alerts coming in. So in either of those cases, we want to develop a set of analytics that are reusable across organizations, because to really be effective in this space, we need to be able to scale. So jumping right into it, this is a bit of an eye chart, and don't worry about the details at all. This is called the Purdue reference model. It's used a lot in industrial control system security. It's a conceptual reference model for an ICS environment. So it's an abstraction, and at the top of this the notional network diagram, we've got an enterprise network, level 5 up there, like you can think of it like any typical business network. And then as we move down the model, we get less involved with the business or the IT portion. Things become more ICS specific. So I said don't worry about the details because we're kind of going to abstract this model up into two sort of layers that we really care about. So in the middle of this model, we've got the green DMZ zone there. We've got level 3, we've got part of level 2. I'm going to refer to those as the OT enterprise or ICS enterprise portion of the environment. And I'll use the terms OT for operational technology and ICS interchangeably. They're not exactly the same thing, but they're functionally equivalent for the purposes of this talk. So in that OT enterprise environment, we've got a lot of things you'll see in a typical IT network. We've got a lot of Windows machines. We've got network protocols like DNS or SMB or HTTP that are going to be familiar. We've also got some things that are more ICS specific. So for example, we might have a historian, which is essentially a database for keeping track of what's going on with the operational process that's happening. Excuse me. And by operational process, I mean the reason we're worried about this environment in the first place, the electricity we're generating, the widgets we're manufacturing, the wastewater we're treating, whatever that process is that we're concerned about. There's going to be specific things in this zone for that. And then as we move down the Purdue layer here, down to the bottom of level 2 and then levels 1 and level 0, we've got what we're calling the process operations section. This is where things become less enterprisey or less IT focused and more focused on that operational process. So in this layer, we might have a human machine interface, so an HMI. It's running on a Windows machine. It could talk to a programmable logic controller or a PLC. And that PLC is a piece of vendor-specific hardware that then is going to actuate a valve or flip a breaker, or it has a temperature sensor on it. It's the thing that talks to the physical environment and lets us manipulate it through cyber means. So again, don't worry too much about this, but the OT enterprise and the process operations layers are the things I'm going to come back to later. So one of the ways we talk about defense, particularly at MITRE, is via the attack framework. Real fast, if you're not familiar, it's a model of adversary tactics. So adversary goals like lateral movement or persistence, and the techniques they use to achieve those goals. So using remote SMB shares for lateral movement or persisting by a scheduled task in Windows. That framework is based on known adversary activity from publicly available intelligence. So things we've actually seen adversaries do in the wild. And we've broken attack up into multiple matrices. So we've got enterprise attack that covers things like Windows and Linux. And then we've got an ICS attack matrix that covers tactics and techniques where there's something particular we want to talk about with respect to industrial control systems. either because there was attacker behavior that leveraged ICS, or because on the defensive side, there are particular things we need to be aware of from a detection and mitigation perspective. So enterprise and ICS attack work in concert with each other. Based on the technologies, enterprise attack is going to be applicable to a lot of this, any ICS environment, particularly at the higher layers of this model, up in that OT enterprise layer. And then ICS attack is going to be focused more on the bottom portion where things become more ICS specific. Although those aren't hard and fast rules, they're generalities. So in general, when we're worrying about defending these ICS systems, I would argue that we should start with the OT enterprise portion of the environment. As a defensive community, it's something we understand relatively well, right? We've got staff that understand these kinds of technologies. We've got tools that can deal with them, right? I know how to process Windows logs. There's a bunch of blogs about any particular security topic you want to dive into. We've got a lot of institutional knowledge built up there. A lot of people who understand these things. It's not always appropriate to blindly apply enterprise best practices to ICS environment, but it's a starting place. And then lower down, as we go lower to the process operations level, you've got hardware and software and protocols that aren't widely understood from a security perspective. So asking questions like, is this ICS command indicative of attack? Is this a bad thing? That requires a lot more work up front. And we'll get into some of that, but just for any organizations that are starting out, I would say, don't worry as much about the operational piece. Start with the things you know and understand. So this is important, not just because it's easier to do, but because in just about all the advanced APT campaigns we've seen, where adversaries attack industrial control systems, they come in through cyber means. They often infiltrate the IT or business network first and then jump over to the OT network. Sometimes they come in via remote VPNs or things, but there's typically some enterprise components involved where we can catch them earlier in the kill chain, as opposed to later on down lower when they're having impacts at the ICS level, down at the process operations level. And it's important to know we're using these two things together. At the ICS community, we love to talk about what makes us special. It's one of the points of this talk today, but it's important to make sure that we don't lose sight of those commonalities and where we can leverage things that have already been done. So for this talk, I'm focused on both these kinds of layers, the OT enterprise and the process operations layer. And we'll talk about some examples from each of these. So I just talked about this reference model. It's nice. It's color coded. It's clearly delineated. I talked about the IT, OT sort of split where we transition from one to another. In the real world, that's not really how things work. You often get sort of messy server closets like this. I've got some statistics down here about poor perimeter security in ICS environments and lack of separation of user management. Because one best practice is to separate out your OT and your ICS environments from the business network in terms of things like Active Directory infrastructure and user management. And you sometimes don't see that. So it's less clean than I presented here earlier. So just a note on that so we're all aware. So I want to talk about some conceptions related to ICS security that I've heard crop up before. One of those is that ICS environments are small and static. And I'll agree that's true in some cases, right? Small town wastewater processing plant or an electric distribution substation. And the same thing I would say holds true in enterprise security. So if you've got a regional paper company, let's say, and they have a small sales office somewhere, that small sales office is probably going to be relatively static. It's not going to be too hard, to understand what's going on there and to deal with that from a detection perspective. I'd say that's not really the environments we need to be worried about. I cherry picked some data here. I grabbed an example from Wikipedia using Duke Energy, which is an electric provider in the US. They do generation, transmission, and distribution, which are three different facets of getting electric, from into your house. They've got millions of customers, hundreds of facilities, probably thousands or tens of thousands of electric substations, all kinds of different stuff going on there. That's the level of complexity we really need to worry about in ICS. It's certainly not any easier than things are in enterprise. In fact, I posit it's actually harder than traditional IT security in a lot of ways. So understanding this kind of complexity and dealing with this at scale is an issue for us. It gets fairly complicated because ICS isn't just one thing, it's incredibly diverse. We've got a lot of different hardware and software and protocols. And then within those, we've got a lot of different configurations of, you might have two sites that have identical hardware and software, but they've been configured differently to do different things. And so they act differently. And the way we need to detect malicious activity in those environments is going to change as a result. Another challenge we have is that domain knowledge is fragmented and it's hard to generalize. I can go out and read a dozen different blogs on, Windows scheduled task usage and probably get a pretty good sense of how that works. In ICS, we've got, pockets of knowledge and we don't have as much expertise. We just don't have the people who understand this stuff as well. These ICS environments are extremely long-lived. Their lifespan is typically measured in decades. So, in enterprise security, you're often dealing with Windows, maybe one or two versions back, but it's not unusual to find stuff that's decades old in these environments. So I might need to go understand how to defend a Windows, XP box or Windows 2000 box. And what are the things that have changed in the last 20 years with respect to Windows security and dealing with all of that is an issue. As well as just, in terms of architectural changes and mitigations, if you want to change something, a lot of times that's not going to happen for years, if not decades. ICS security, the ICS community sort of understands security the way I think we did in enterprise maybe 20 years ago. They're kind of getting the message that this whole cybersecurity thing is important, but both at the executive level and down at the the operator level, the person who's in the weeds dealing with the actual equipment, there's still a lot of education to be done on why cybersecurity matters, why it's important, how to actually detect and defend this stuff. And then from a technical perspective, we often have difficulties with data collection. So, 10 years ago, there was less EDR, endpoint detection and response in the enterprise market. We were kind of just waking up to the fact that we need to do endpoint detection as a community, and we've come a long way, in that time span. On the ICS side, deploying endpoint sensors can be really difficult. Sometimes you'll get hardware from a vendor, and maybe it's like I mentioned a Windows HMI earlier, and they might say you can't add any additional software to this HMI without avoiding the warranty. So, putting additional sensors on there might be a non-starter. Or, you might have a plant manager who says, I can't accept the risk that you're going to put more software on this machine, and it's going to cause some instability, in the process and cause, millions of dollars of downtime or, even loss of safety or something. So those typical best practices in enterprise can be much more challenging in ICS in terms of how we're monitoring. So passive network collection often becomes a lot more important. We've also got issues with like remote systems, scalability. So I mentioned Duke Energy earlier. They've got thousands of substations out there. That might just be a shack in a field somewhere with a couple of PLCs and a cellular connection. So it's not like we've got a data center we can go monitor and we're done. We have to deal with remote sites with bandwidth constraints, a lot of unmanned sites. So people might not be at these places regularly. So if something goes wrong, with a network sensor and they have to send somebody out, that's a bad day. Another issue with data collection is proprietary protocols. So these ICS protocols, sometimes they're open specification and sometimes they're completely proprietary. And the vendor put out a protocol and doesn't tell you anything about how it works. And even with the open protocol, sometimes we get vendor-specific protocol extensions. And there's a place in the spec that says, this range is reserved for vendors to implement, whatever they're going to do. And then that's something we have to deal with as we're understanding these environments and figuring out how to detect malicious activity within them. So continuing with the challenges, in enterprise security, we've got a lot of data points on APT activity, on security threats we've seen. We've got a huge attack matrix. On the ICS side, we have maybe half a dozen real incidents that involve APT actors. And then even within those incidents, there's a lot of places we know we're missing intelligence. So maybe we saw them do some activity in an ICS network, but we don't really know how they got in. We don't know how they did collection and discovery. we don't have logging for that, or maybe the attacker erased some data, or it just didn't end up in the finished intel for some reason. But there's a lot we don't know. So as a corollary to that, and this is more of an attack specific thing, attack maps high confidence behaviors, which is appropriate for what it does. But in the intel, oftentimes we'll say, we'll say, an analyst will say, we saw them get onto this machine, but we don't know how they found this machine. We didn't see any discovery activity. And so that kind of assessment isn't going to make it into attack, but it's important to know that, that's a gap we have, and maybe we can posit some of the things they did, and we can make some assumptions as defenders. But we can't just blindly rely on our models and abstractions. We often need to go into the source intel to really understand as many details as we can about what happened. And then taking this information from intelligence or from public reporting and turning it into actual TTPs, into behaviors we want to defend against, is challenging. The environmental diversity, like I mentioned, is huge, and understanding how how an attack that occurred elsewhere might play out in this environment you want to defend can take a lot of work. And this is where adversary emulation becomes particularly valuable. We can go in, do some emulation, and think about how this attack might look, in my environment that I'm trying to defend. Excuse me. Sorry, my allergies are acting up. So I've got some ICS data sources here. Let's start with just host and network data sources. I've got two boxes in there that say enterprise sources and enterprise protocols. So in those boxes, I'm thinking about all the things we typically do in enterprise or IT security, where we've got host and network-based monitoring. So, Windows log collection, commercial and open source tools like Sysmon, standard network monitoring. You've got open source tools like Zeek or Suricata. You've obviously got various commercial solutions. So that's what in those top two boxes for host and network for the enterprise portions. Diving into some ICS specific details on the host side, I've got ICS device and application logs there. So, for example, this might be a piece of vendor software an engineer uses to do maintenance on a system, or logs from a PLC, a programmable logic controller, about what actions it's taking. And those are going to be logs we can pull off and potentially do something with. But as you might be able to tell from what I'm talking about, it's going to be vendor specific. It's going to depend on what software is running, on what logs are even available. And that's going to then inform how we can approach, defending this product line or this manufacturer or this particular site I'm worried about. Likewise, on the network side, we've got enterprise protocols, SMB, RPC, HTTP, pick your favorite protocol that we understand how to deal with relatively well in most cases. We have network parsers for them. Then we've got ICS specific protocols. I'm going to talk about IEC 104 a little bit, and DMP3. There's a whole slew of different protocols for different kinds of industrial processes. And so one of the challenges is that we don't always have network parsers and tooling around those. And then even when we do, they don't always extract the data we need. So that's general host and network-based collection, a lot like you'd see it in enterprise, although obviously with some tweaks. We've also got this third category of operational sources. And this is things like operational process alarms, like, hey, the temperature in the oven is too high, or there's not enough water flowing through this pipe. Operational process data, just about the process that's going on, and are things in variance or out of variance. Asset management is often big in ICS systems, so not just what PCs and laptops are in my environment, but tracking hardware and knowing that I've got this PLC and I've got 3 replacements in the back in case I need to swap something out. Those kinds of management systems can be helpful for environmental context, understanding what's going on. Another useful data source could be work order tracking. So in these environments, you get a maintenance request to go replace a piece of equipment or change some values with the operational process. Maybe you're spinning up a new manufacturing line. So this kind of business tracking of what changes are going on in the environment can help then inform our detection engineering. So these operational sources complement the traditional host and network-based collection. As I mentioned earlier, as you're moving down the Purdue model and moving into that process operations level, you're getting closer and closer to the adversary impact. So like I mentioned earlier, starting with the OT enterprise portion, when you're doing defenses, because that's earlier in the kill chain, these operational sources are generally going to be later in the kill chain. So they're valuable, but you need to understand sort of how they fit into the bigger picture. And I would say not just to rely on them solely. So I've got a simple network skim here for we're talking about ICS protocols. At the top level, we've got the protocol itself, which we're using when we define requirements. So, I mentioned IC 104, DMP3, I've got BACnet up here. Every one of those protocols is going to have some concept of a function. So just like you can use the FTP, the file transfer protocol, to read a file or write a file or list a directory, each of these ICS protocols is going to have some concept of doing reads and writes, maybe updating firmware or pushing a file or resetting a device. And those capabilities are going to vary, but they're all going to have some concept of that. And that's what we're calling the function code level. I want to read something, I want to write something, whatever the case may be. And then the next level down is the payload level, which really defines the interface we need to populate. So the example on the slide here is the BACnet protocol, the read property function. And then if I'm reading a property from a BACnet controller, I need to pass it a bunch of information. I need to pass the device, tell it what object type, tell it what, the address I'm reading from. There's a bunch of information I need to populate there. So understanding each of those three levels helps us then define detection requirements, which informs what data we parse out, what data we retain, and what we really need to be able to do to defend these networks. So just walking through a quick example at the top, we've got a protocol, DMP3, which is a protocol used in North American power distribution. So if I've got a controller that speaks to DMP3, I might want to know when new clients are talking to it, because that would be unusual and might be indicative of malicious activity, right? Or it might be a configuration change I want to know about. Down at the function code level, maybe I want to know when new DMP3 read commands are issued, right? A new device is issuing a read command. That's unusual. That might be indicative of adversary collection in the environment. And then down at the payload level, I want to not just there was a new read, but what was being read. And depending on the ICS environment, that might be a relatively static thing, or it might be all over the place. So how this detection really applies is going to depend on the environment and what's being monitored. So as we go down the stack, we're asking more detailed questions of our data, and then we have to do more analysis, both from a machine network parser perspective, also a human analyst perspective. And then it's becoming more specific to the environment. So we get more insights, but there's additional cost there. So I mentioned there are a lot of different ICS protocols. They're not all used interchangeably, right? So I'm going to talk about the IC 104 protocol. It's widely used in the Middle East for power distribution, and it was specifically targeted in an attack that occurred in Ukraine in 2016, where we saw the Sandworm Activity Group, which has been tied to Russian, I believe the GRU, attacked Ukraine and caused some widespread power outages with the Destroyer malware. So naturally, a lot of folks in the rest of the world were worried about this attack happening elsewhere. In the US, like I mentioned, we don't use IC 104. We use DMP3 as one of the protocols. So to really understand how an attack like that might manifest in the US, we need to understand what the adversary did with IC 104, and then how those same things could be done with DMP3 in our environment. So obviously got the protocol at the top there. Down below, we've got a bunch of functions listed. In IC 104, we saw them use the select and then the execute command to do some profiling and manipulate some circuit breakers on the PLCs. So in DMP3, we've got a number of options for how we do that. We could use select and operate commands, or we could use the direct operate command. And those have some different semantics. And what's expected in a particular environment, again, is going to vary depending on how it was set up. So this adds some challenges. It also gives us another opportunity for detection, because if normally my environment uses select and operate commands, and all of a sudden I see a direct operate command, that should stick out. But there's a lot of research and effort needed to get to that point, right? This isn't the kind of analytic we can just deploy the same way you would a traditional, Windows process creation analytic, for example. Then below the function code level, as we get into the payload level, things become more environmentally specific about, how these payloads used, right? What addresses are being read off the device? What DMP3 class object is really relevant here, and what are the indexes? And just, essentially, how do I address the piece of memory I want to read? So we can do some good work at the payload level that's reusable, but it takes more effort, and we have to think through things a little bit more, and probably do a little bit more tuning per environment. So I'm going to jump back up to the OT enterprise level for a moment and talk about a Windows host-based perspective. So this is creating a new service, and the graphic on the screen here is called a capability abstraction. This is something, a concept that SpectreOps put forward that I really like. So I'm going to talk through this and then talk about how it applies to other ICS use cases. So real quick, we've got an attack technique at the top, Windows service creation, where adversaries will go in and create a service for persistence or for privilege escalation. And there's two sorts of broad sets of procedures you can use to do that. You can directly create a service, either using built-in Windows tools or third-party tools, or you can actually sideload a service by just directly manipulating the registry. If we go down a level under direct service creation, there are a bunch of tools there. Like I mentioned, some of those are built in, and then they each have APIs and RPC interfaces they use. Those tools all culminate down at the service control manager, right? No matter how you get there, you're going to end up going to the service control manager, which is actually going to handle creating the service legitimately in Windows, and ultimately creating a new registry key. So how is this useful for detection? One thing we can do is put a bunch of logs on here and look at what logging sources we can get out of each one of these pieces of data abstraction. So up at the tool level, we've got things like process creation logs, which are Windows event log 4688 or syslog log 1. There's some things we can do there that are maybe a little more specific and have a lower false positive rate, but then they're going to miss activity. I'm just looking for invocations of sc.exe. I'm going to miss psexec, for example. But as you know, the service control manager down there at the bottom covers a lot of this activity. So that what SpectreOps refers to as a choke point can be used to catch a lot of different adversary procedures. Of course, if you're doing the other procedure here, you're sideloading by a registry key, that service control manager isn't going to help you. You're essentially bypassing that. So just understanding that sort of adversary trade space and what maneuverability the adversary has is important for understanding what your detection looks like. Another thing we can do here is, list adversary procedures. So in Ukraine, the Ukraine 2016 attack, we saw them use sc.exe to create a new Windows service for persistence on it was an HMI engineering workstation that was talking to these ICS assets.
So Michael,
yes.
Quick question, interrupting for a quick question, but I love this chart. So it sounds to me like, you're showing how these, this combination of areas you can observe on your victim network can help you piece together, if you understand how these various data from these logs would fit together, correct?
Mm-hmm. Yes.
Cool. That's just sharing. That's one of the key focus areas of this working group, is sharing those connections and correlations. And so I think there's a really good overlap here. And I thought this was a good spot to stress that. So just wanted to share that with you, that's some of the work that a lot of us here are working on right now. And I think this is a really powerful combination. And Harley wanted to chime in as well.
Yeah, Charlie, thanks. Yeah, and just one additional point, and I think, Mike, you made it very well, is there is that trade-off between getting very specific and looking for certain aspects of these procedures versus and where you may actually miss kind of a slight variation of the attack compared to something that's so generic you get a lot of false positives. And I'm curious Mike, from you and Nick on your view of, I think that plays out very well in your example here with the OT enterprise. And if you're going to address it later, but as you get down into the ICS operations layer, whether you see the ability to get into that sweet spot of being able to limit or being able to generate these detections that aren't so signature specific that you're going to miss other variations of it. I don't know if I made a lot of sense there, but
yeah. So certainly, I think I'm glad you sort of called that out, because I mentioned that and didn't expand on it. Sort of that tension between false positives and false negatives, and at the top of this abstraction, you are going to detect things that are more precise, but then probably miss some stuff. That same tension we have is something we deal with at the process operations level. Looking for these kinds of attacks, down within the ICS protocols. And I'll talk a little bit more about that later. But it's definitely a concern all the way through.
Also, not to add any stress on you, but we're probably got about a little bit more than 10 minutes before we can have some time for Q&A. So we
Okay, thank you for watching the clock. I have a lot I wanted to get through, so I'll speed it up a little bit. I wanted to share this anecdote about some work we did last year with the BACnet protocol. So there's a concept of writing a file over BACnet using an atomic file write function. And there was one open source implementation of BACnet that we used to do some estimated emulation. It would write the file, and the files we're dealing with were on the order of 10 or 12 kilobytes. And so we said, okay, well, we could probably use bytes transferred as a proxy for understanding file transfers in this environment, and that'll probably be good enough for detection. But we found when we started digging into things is that the implementation we were using really differed from the specification. So the tool we're using pushed an entire file, you give the file name, it wrote the file name to the file itself to the controller. But the specification says that you can write arbitrary bytes of data into whatever offset in the file you want, right? So I could write 5 bytes in the middle of the file, and spec will happily allow that. So there are cases where this could be important. And so understanding that the implementation and specification are different, and we really need to understand that specification, understand what maneuverability the adversary has. So bringing this back to the capability abstraction, I've got BACnet here. The behavior is using BACnet to write a file. And this second row down there, where I've got program download, modified program, those are all ICS attack techniques. And there are so many of them there because BACnet files can do a lot of different things, again, depending on the vendor and on the configuration. So the spec says that there are 2 different ways to write a file. Stream access is what I talked about, where you're writing an entire file or you're writing a chunk of a file. There's also this other concept of record access, where you're writing one record at a time and you're writing this higher level data structure, right? And that's going to manifest completely differently on the wire. So you need to understand as you're parsing out this data what this looks like. So again, it's something we have to deal with from a parser and environmental perspective. Also might be an opportunity for detection if you start seeing unusual methods of writing files. And again, it kind of goes that false positive, false negative thing of, if the environment is more dynamic, maybe I need a more specific detection. I'm willing to, tolerate some misses, some false negatives. So I'm going to dive a little deeper into some additional work we did last year using the TCHAMP threat hunting methodology. So this is a methodology Motive created. It's not specific to industrial control systems. We used it with a number of government sponsors for different kinds of environments. So real quick, it starts in the upper left with a malicious activity model. In our case, that's attack. From that model, we pick some behavior we want to develop detections around, and then we develop hypotheses and abstract analytics, some general questions we want to ask about this behavior to detect it in this environment. All right, I'm going to look for X and Y, Based on those questions, then we determine what data we really need to collect. And then that brings us up the right side of this view where we're operationalizing this. And we say, okay, well, I'd like to detect, these Windows logs and these fields of network traffic, but, my tooling doesn't let me do all of that. So either need different tools or I need to revisit, how I'm going to detect this behavior. Then from there, you implement test analytics in your go off and you hunt for malicious activity. So in the Ukraine 2016 attack, we saw a number of different enterprise attack techniques used. A lot of these are Windows living off the land techniques where there wasn't custom malware. This was just using built-in Windows services. And many of these are the same things you'd see in any enterprise environment. Creating or modifying a system process, using valid accounts, using a proxy, kind of standard enterprise stuff. Although there are some ICS specific things we need to be aware of. So for example, they created a new account on the Microsoft SQL historian that was in the environment. That's the database that watches the operational process. In an ICS environment, that historian talks to a lot of things, so it made a good pivot point for them. And so they created an account there. So knowing that and looking for that kind of activity, I probably wouldn't look at every single database server in an enterprise and look for new accounts there. But well-connected historians in an ICS environment, it's something I'm going to want to pay more attention to. So we can't just blindly apply the enterprise best practices and detections here, but they do serve as an excellent starting point. And this is diving into the ICS matrix. So I've color-coded it here and broken up into different buckets. And what we're trying to do here was some prioritization around where do we think we're going to see good generalizability and reuse in our detections, and where are things going to be more specific. So some of these techniques were more based on Windows on the OT enterprise side or in IT protocols. So we're expecting pretty good reuse there. Some of them were more specific to a SCADA, basically a controlling process that's monitoring the ICS environment. Some of those are going to be specific to that hardware and software or specific to a particular environment. And some of the detections are going to be more based around the OT protocol or the ICS protocol. And we should see some good reuse there as well. So again, this is just us trying to prioritize and understand where should we start if we're looking at 24 techniques. How do we narrow this down and try to find good generalizability? So we went through, we created a number of abstract analytics and hypotheses. And the important thing was we listed out our assumptions about how those apply to our environment. So for example, if I've got a HMI, human machine interface, is speaking DMP3, is that over an Ethernet connection that we can actually monitor and we can stick a network sensor on, or it's going to be over a serial line and I don't have any visibility there. So then I have to revisit and figure out something else. Because that is going to vary. And so listing out how this attack is going to manifest and what kinds of defenses we think we can, or detections we think we can generate and what data we can collect. That's an important part of this process, just listing those assumptions. So I've got an example here. So starting on the left, we're looking at point and tag identification. And the procedure we saw in Ukraine 2016 was using the IEC 104 commands to do some profiling and discovery and figure out what was going on the PLC. Our adversary emulation behavior in a DMP3 environment would be actively inserting some integrity holes. And then based on that emulation, I can do a number of different analytics, either function code anomaly detection or even lower level payload level anomaly detection, taking some extra features into account. And that's going to change my data requirements. So if I dive deeper into this and split up both the function code and the payload anomaly detection, I might come away looking at looking for a high volume of reads in one case, or maybe a change in periodicity, so a change in the inner arrival time of reads. If they're coming in on a schedule and that schedule changes, that might be interesting. And likewise for payload detection, there are going to be other fields that I want to pull out there, depending on what I'm looking for. So that then gives me more detailed data requirements I can start writing collection requirements against. Excuse me. So given those detailed data collection requirements, I can then say, all right, what analytics can I really build from this? If I'm looking for high volume of reads, that might be reads from a new device. If I mean reads, from to a single device, either above or below a previous threshold, or it might be across a wide variety of devices. I'm doing some scanning. I'm talking to dozens or hundreds of devices. So, that seems kind of straightforward when I say it like that, but the idea here is that we started with an adversarial behavior and we took it all the way through to this end product of some relatively detailed analytics. And I'm not too worried about how we're actually implementing that anomaly detection at this point. The idea here is that there are a lot of different vendors that offer products in these spaces. There's a lot of open source tooling. That's a problem, and an engineering problem we can solve. I've got traceability, so I understand how I got to that requirement. And the next time an attack comes up, I can go, oh yeah, I understand that behavior. I've got a detection that works for it, or no, this is a different attack and my current detections don't work. I need to revisit some of my assumptions. Then it also informs data requirements for collection and retention, like I mentioned previously. So that was, a single detection, and analyst is going to get that an alert off that and going to then need to determine, all right, is this malicious or benign? And there's a whole bunch of questions they're going to ask. So we also need to think about what context we're providing analysts, both in the alert itself and then additional dashboards or visualizations we want to provide. So things like normal rate of read operations, or what kinds of objects are normally read from these devices. Other indications of activity that's going on in the environment. Maybe I've got something that's suspicious like this. I then layer on other analytics that have more false positives. So they're not good as like a first pass indicator, but when I start to have multiple lower confidence indicators that something is going on this device or with this account or whatever the case may be, that's a more interesting finding. So that was a lot of information pretty quickly. I know I had kind of speed up there, but I talked about detection engineering, how we need to use adversary emulation and purple teaming, the importance of analyst context in these environments and operational context about what's actually going on beyond just getting an alert and then not being able to do anything with it. And both from an adversary emulation and a detection perspective, how just taking existing tooling and running with it isn't really appropriate. You need to understand what capabilities an adversary actually has in these environments with the hardware, software, and protocols. So with that, I will, pause for additional questions.
Thank you very much, Mike. So let's open floor for a few moments. Does anybody, Harley, jump right up. Go for it.
Yeah, you knew I'd have a question. So Mike, very good talk. I appreciate your insights. One of the things I'm trying to grapple with a bit is how, as we're focusing on looking at the generation of detection and detection objects for the enterprise, being able to ensure that you have consistency across one environment to another, right? So, you may deal with Windows or, various Linux versions, but what you have in Windows is always Windows. It's easy to detect and it's going to be consistent from one to the other. But when you're dealing with some of your process control layers, I'm curious about a detection, as you mentioned, a lot of different vendors in that space. And, do you see consistency between the implementation, say, of vendor A's DNP3 protocol to vendor B's, or some of those aspects that you'd want to be able to write your detections in a bit of a more generic way and not be so tied to a particular vendor product?
Yeah, so that's one of the things we were trying to target when we looked at this ICS attack mapping and looked at the OT protocol here in gray, was that you do see good, to some degree, good reuse of detections and good interoperability between devices with these open protocols where we understand what's going on. So that is one of the ways I want to try to, as a community, I think we can generalize and write things that have good reuse with hopefully some minimal tuning between sites.
Okay, good.
Did that answer your question?
Yeah, it does. And I guess if you were dealing with something, maybe a PLC layer versus the network protocol, or some of those type of things. You see similar consistency there?
So the internals of a PLC, how they work and firmware and those kinds of things tend to be more vendor specific.
Right.
Yeah, I guess, Nick, do you have any insights here? My background's actually more on the network protection side, so I'm not as familiar with the hardware piece.
Yeah, so it's a great question. I think the easiest way to answer it in my mind is, an example of the table that Mike presented, right? When Mike talks about the capability abstraction, really what that becomes is the codified artifact of our understanding of how this specifically operates in this environment. We use that simplified schema at the protocol function or payload, and that really gives us the rough tear line, if you will, as to where we can build a parser from the defensive side of things that we have a high level of certainty is going to transcend environments. So for instance, if I go into an environment, I can now start at the function level, say, and identify, hey, has this vendor implemented it the same way we've seen in other environments? Oftentimes we see the answer is yes, right? And we'll deal with the payload as the last piece. So that gives us an enormous value proposition to say, if we build detection logic that provides 90% of the puzzle to the defender at the end of the day at the function level, man, we've got a real high level of reuse. But a lot of the detection logic that we're seeing people focus on is so acute, it's all the way to that payload level. And that's why we see such a lower level of reusability. So generally, the first piece is starting at that function level. To answer your second question, then, Harley, is do we see differences from function to function? Yes, we do. However, I think the largest portion of differentiation we've seen is just certain functions being used or not. And really what this means, right, in the table that Mike has here, this is showing that a single function can be potentially aligned from an adversary perspective with 6 or 7 different techniques here. Well, the same thing holds true if we look at the other way around. I can leverage several different functions in order to achieve a specific effect. That doesn't mean those operations are going to be quote unquote normal or based on a typical or indicative behavior of how my operational system works. So just the presence of those functions alone is something that we on the defensive side can use to say, this adversary doesn't understand that these functions are not typically used for these control operations. So that's really where I think we've seen the lion's share of differentiation at the function level.
Okay. No, I think that thank you, Nick. That's really good because our thinking as we've been looking at this is trying to define, at least for within enterprise environments, define those detections not at the tactic or technique level, but trying to get to the attack sub-technique level where you get a little bit more specificity in terms of what you want to look for, but you're not so down into a low-level procedure that you're going to start missing a lot of things. So it sounds like with your function level versus payload, you're kind of along the same lines of thinking. Would you agree?
Yeah, I think that's exactly it. And really, oftentimes the mantra that we come to is operations first, then security, right? That's a critical differentiator when we go into ICS environments. This table that is listed here is an artifact that we use for understanding normal workflow from a security perspective. So coming back to the original question, how do we help identify false positives and whatnot? It's this table. If I understand that one of these paths is the green path, if you will, that's how operations typically occur, I should exactly use that to create workflows for triage processes, for IR, for threat hunting, to understand differentiation. Because A, I'm learning new things about my environment. Oh, wow, these other methods are used and I didn't know. Or B, we're explicitly saying that behavior is something I need to seriously run down because it wasn't expected.
Excellent. Thanks. Sorry, Charlie, I think I may have taken up all your time.
That's okay. I just wanted to thank again Mike and Nick for this today. It was really useful, and invite both you guys to join up on the Slack for the working group, because I do see a ton of overlap on the same type of challenges we're dealing on the enterprise space to the way that you're going after these challenges with your abstraction in ICS. And I think it's a good idea. Like, I think we'll get some good ideas off each other, and I'm grateful for you taking the time today to go over this with us. So thank you all very much. Yeah, we're a little short for general discussion today, but if anyone has something they need to ask in the next 60 seconds, I'm glad to help field that. Otherwise, I'll invite everyone to come back in for the July meeting. And I'll be passing out the notes on the listserv and the Slack afterwards. And this should be posted up on YouTube relatively soon if you want to share this great talk. Any last second questions, anybody? All righty then. Thank you again, guys, and everyone have a fantastic day, and we'll see you next month.